Remember the importance of the oxidizing, reducing definitions is really important because we have to be able to identify them all the way through basically for the rest of this unit. So in this case, oxidation, we have to remember, involves a loss of electrons, whereas reduction involves a gain of electrons. For this particular exam, or for this particular class, the College Board does not want you to identify the oxidizing or reduction agents any longer. I don't know how to, like, I don't know if there's some cutesy little way to say remember what means what, because like oil rig or Leo goes grr, both are, for lack of a better term, cutesy. But like it still is confusing. So sometimes I like to think of it in my head as like, oh yeah, reduction. Once I figure out whatever the thing is in terms of reduction, it's opposite of that. So of what it sounds like, if that makes sense. So in my head, when I was learning this, I remember thinking to myself, reduction, that's when you lose electrons. And like I had to remind myself over and over and over and over again that reduction means a gain of electrons because it's a reduction of charge. So that's kind of how I try to keep track of it inside of my head, which, as you guys are aware, dark place sometimes. Now, we are going to focus on voltaic cells today, so I need to kind of spend some time talking about them. So the first thing we need to talk about is what actually a voltaic cell is. And a voltaic cell always has two electrodes which link the cell with the surroundings. The first electrode is an anode, the other one is a cathode. And I am sure at some point in your academic career you have heard those terms, but we have to define them for chemistry. And in this case, the anode is the compartment or the cell where oxidation takes place, and the cathode is the compartment or cell where reduction tends to take place. So remember, reduction is a gain of electrons, and oxidation is a loss of electrons. And we're going to come back to this in a couple of times today, but I'm telling you right now that you need to know what an anode is in terms of where oxidation takes place and what a cathode is in terms of where reduction takes place. Just something you have to know. Also, another part of the voltaic cell is the electrolyte solution. That's composed of a mixture of ions that are involved in the reaction and work to carry charge. Although one of the ions that's going to be involved is going to basically be a spectator ion. And for our practical purposes, if I ever ask you to draw a cell, I think that you might want to use like nitrate, because nitrate is never involved in anything. It's always soluble, if that makes sense. But we'll talk about that when we actually draw a cell later. The voltaic cell also needs a wire that connects the cells together. Oftentimes, the wire is drawn as having some type of a voltmeter part of it, and the electrons always flow through the wire. They don't do anything. They don't go anywhere else. You also need a salt bridge, and we'll talk about the salt bridge in a minute, which is generally an upside-down U-shaped tube that's filled with a non-reactive salt solution. A non-reactive salt solution like NaCl, for the sake of things being easy, or some type of semi-permeable barrier that lets ions diffuse from one side of the voltaic cell to the other side as some type of a wick, like a wicking material, if that makes sense. If by chance both half reactions happen in the same beaker, no work can get done, but if the half reactions are separated by two half cells, work is able to be done by measuring the current moving between them. Any questions about that? Here is a schematic of a voltaic cell, and we're going to kind of spend a little bit of time talking about this. So I'm going to start with the copper cathode over there on the right-hand side. So here is one of, on this right-hand side, I have the cathode side of this voltaic cell. In the cathode side, I have 1 molar copper nitrate solution, okay? On the anode side, there is a zinc anode, and in this beaker, I have 1 molar zinc nitrate solution. Do the solutions have to have the same anion? No, not necessarily, but whatever anion is chosen has to be something that's going to be spectator-ish, okay? Now, the other thing is that there is the wire that is connecting the cathode, or the anode rather, to the cathode side, and in this case, it's separated by a voltmeter. which appears to be measuring 1.1 volts. Note the flow of electrons is from anode to cathode, and what's occurring here is really important. And we kind of saw a slide about this yesterday, but what's occurring here is really, really important. So if I start at the anode side in this blown up section right here, what I see is that my solid zinc is losing 2 electrons, and those 2 electrons are going to travel from the zinc anode to the copper cathode. But in the process of doing that, this zinc atom that lost its 2 electrons now gets put into solution as zinc ion. And on the product, or on the cathode side, the electrons, as they come down into the cathode, what they end up doing is they end up, hold on. Sorry. Whew. What they end up doing is we end up with a buildup of electrons, and as a result of that, the copper ions in solution are now going to pick up these 2 electrons, and they are going to become solid copper. Okay? The other thing that is present here is the salt bridge. Thank you. Is the salt bridge. The salt bridge is that upside down U-shaped piece of glass tubing that is full of, in this case, salt water. So the salt bridge in this particular case, all that we do when we set this up is we take a U-shaped piece of glass tubing and we just fill it with salt water and put our fingers over the holes. And then what we do is we invert it and jam it into the separate beakers just like it's going on there. And the reason for the salt bridge is to kind of keep the circuit connected. But I'm going to try to explain very quickly what's going on here. So note that in this case here, as the copper ion is picking up electrons and going into the solid formation of copper, the net charge of this neutral solution is now down a +2. And as a result of that, the positive sodium ion gets pulled into that solution to keep it being neutral. And on the zinc side, okay, when we take the neutral zinc atom and it becomes the negative zinc ion, what ends up happening is that this side becomes a little bit negative, and as a result of that, we bring some, or I'm sorry, this should be positive. I don't know why you can't see that. But it becomes a little bit positive, and as a result of that, we pull some of the chloride ion down to keep it neutral. Does that make sense? Questions about this now? Okay.
But we have to know how it works.
Yes. You're also going to have to be able to draw it. And I'll go through an example of that in a minute. Yes, sir.
Can you explain why the chloride goes onto the zinc side and the sodium goes onto the copper side?
Okay, so we start with copper solution, which means we have Cu+2 aqueous floating around, right? As those copper ions pick up the electrons and become solid copper, the solution itself, which was neutral, now has a negative charge. So the sodium ion in the salt bridge is going to replace the copper ion, okay? And on the other side, when the zinc comes off of the zinc anode, it is adding a bunch of positive zinc charge. And so the chloride ion comes in to offset that so that everything remains neutral. Now, in theory, this reaction will continue to go until either all of the anode is used up or all of the cathode solution is used up. And I'm going to show you a picture in a second here of an anode and a cathode. So the anode appears to have lost some mass. Hopefully you can see that in that picture. And the cathode appears to have gotten a little bit thicker. So this is evidence that the zinc atoms are coming off of the solid zinc anode, and the copper atoms are attaching themselves to the cathode. Now remember, this mass change occurs when atoms from the anode move into solution as ions, as they lose their electrons, and the electrons that are gained on the other side pull the ions in solution and form solid atom, neutral atom on the cathode. The other thing that we have to remember is that the mass changes are not the result of electrons themselves, because electrons are the smallest of the three subatomic particles, and they barely have any mass. So the mass change themselves is really the atoms either coming off of the anode, or they're being added to the cathode. Sorry. What? Okay. So because electrons are so incredibly small, even though they're being transferred from one side of this cell to the other side, they're not the reason why we have a mass change. The mass change is really because the zinc atom is being removed and becoming the zinc ion and going in solution. And when the copper ion accepts those two electrons, it's adhering itself to the cathode, and as a result of that, making the cathode have a little bit more copper atoms. Yes, sir?
So the anode is always the one that loses the mass, like there wouldn't be a situation where.
Correct. All right, moving on. Sometimes you'll come across voltaic cells that have inactive electrodes. In this case, the inactive electrode, or the anode or cathode, is copper. Actually, not copper. It's carbon. More specifically, it's graphite. So in this case, what ends up happening is that as the electrons are transferred, in the case of the anode, what ends up happening is we get solid iodine that forms on the anode, and what ends up happening on the other side, the cathode side, is we get a darker solution in the cathode side. But we don't spend a lot of time talking about these in this scope of this class, so I just want you to be aware that you can have inactive electrodes that don't change mass. When you are asked to write the notation for a voltaic cell, there is a very specific format you have to follow, and it is what's drawn here. You're not going to always be drawing these cells specifically because they take up a lot of room, so this is the easier way to do it. The left-hand side of the voltaic cell notation is always the anode, the oxidizing side, and the right-hand side is always the cathode, the reducing side. And it further is broken apart into the phase of the lower oxidation state followed by the phase of the higher oxidation state. And then the phase of the higher oxidation state of the cathode followed by the phase of the lower oxidation state of the cathode. So an example would be in the case of the zinc to copper, here's my half reaction for zinc, and here's my half reaction for copper. The lower oxidation state of zinc is the 0, and the higher oxidation state for zinc is the +2 ion. And the higher oxidation state for copper is the Cu +2 ion, and the lower oxidation state is the copper. Okay? So that is the format in which you would write voltaic cell notation. If by chance you have an inert electrode, one that doesn't react, non-reactive, you simply add that to the end of it. Okay? But in this case, in the case above, the electrode itself, remember, is the solid portion. Yes, Megan?
What did you say was the lower oxidation state?
For zinc,
Yeah.
the Zn, 0, no charge. Questions about that? Yes, sir?
You said the inert electrode goes at the end?
Yeah, so because it doesn't really, it's not part of the reaction.
Why is that the beginning of that one?
Well, I guess I meant end of the left side and the right side.
So it begins at the end of
yeah, I guess it sandwiches it. That might be a better way to say it. It's a graphite sandwich.
Sounds pretty decent.
But you wouldn't call it a bread sandwich?
Bread sandwiches would just take.
No, I don't really eat a lot of bread. Yes?
No, can you explain which one the lower and higher oxidation states again?
Okay, so when you're assigning oxidation states for monoatomic atoms, right? This one would have an oxidation state of 0 because there's no charge. This would be a +2. This one, here's my 0 and here's my +2. Now, is it always going to be 0 and +2? No, but it's based on the oxidation state that you would assign based on the half reactions. Does that make sense? Pardon?
Yeah.
Okay. So at some point, you're going to have to draw one of these guys. So we're going to work through that in a minute here. But the very, very first half of this that you're supposed to do is you are supposed to go ahead and write the half reactions for the following system. So in this case, I know that the magnesium side is my anode side because that's the notation. So anode is the side that tends to lose electrons. So I'm going to write it like this. So I'm going to have magnesium will lose electrons and become the magnesium ion, and I have to show that it lost 2 electrons. So there's the half reaction. And on the other side, I have aluminum ion that, in this case is a +3, is going to gain 3 electrons to become solid aluminum. So, given the format, it's pretty easy for me to figure out where the electrons are going. Okay? Now, like I said, at some point we're going to have to draw one of these things, so I'm going to try to do my best to draw one of those things now. So, I'm going to start with my beakers that this will be occurring in. So I'm going to have a beaker here. That's an awful beaker. And I'm going to have another beaker here. That's a little bit better, I guess. Okay. Now, the other thing, oh, geez, that's going to happen. Those are really far apart. Is the other thing that's going to happen is I need to have a salt bridge. So I'm going to draw my salt bridge that separates, or that connects these guys. And that's going to be, I'm just going to use NaCl because that makes a lot of sense to me. Okay, and then I'm going to need an anode. So on this side, I'm going to draw an anode, and I'm going to need a cathode. And on this side, I'm going to draw a cathode. And then I'm going to connect them with a wire. So here to like here, and I'm going to throw a voltmeter in there. Because why not? Okay. And let's see, is there anything else I need to draw? Oh, I should probably draw some solution. So I'm going to draw a little bit of solution over here. And I'm going to draw a little bit of solution over here. Okay, like that. Lots of fun. Now, we know that the cathode in this case is going to be aluminum based because that's this side of the reaction. So there's my aluminum. And we know that the anode is going to be magnesium based. So magnesium right there. Okay, I don't like the way I have it. Magnesium. Okay, now I also have to have some type of a solution, and so in this case, to like make my life a little bit easier, I'm going to make Mg NO3 2 solution. So that would look something like this. I'm going to have 1 Mg plus 2, and I'm going to have some NO3 floating around, NO3 minus and NO3 minus. And then on my aluminum side, I also have to have some solution. So I'm going to have Al NO3 3. So I'm going to have some Al floating around, some NO3 minus, some NO3 minus, and some NO3 minus. And then lastly, I have to do something with my sodium and my chlorine, okay? So I'm going to identify that the sodium, in this case, +1, chlorine, in this case, is -1, and I'm going to show that the sodium is being pulled there and the chlorine is being pulled here. The last thing I would probably want to identify is the flow of electrons, and in this case, my electrons are traveling from anode to cathode, and I should probably label that as well. So here's my anode, here's my cathode, and there's your template for every single voltaic cell. Voltaic cell, V-O-L-T-A-I, sure, I don't know. For every voltaic cell, every single one. They should look the same, except the letters are going to be different. Does that make sense? Any questions about that? How do we feel about, yes?
In this case, since the aluminum has a +3 charge in solution, why would the Na+ be pulled here still?
Oh, I might have put those backwards.
No, because the other side is Mg+2. So
Because, no, remember, the aluminum is being pulled toward and being removed, right? So the aluminum is being removed, and because the aluminum ion is being removed, there's less positive charge. So we have to put that sodium positive charge in at a rate of 3, okay?
What about the Mg+2 then?
So the Mg+2 is being made, and I'm adding chlorine to it to bring that plus down.
So there's still Al+3, it's just that.
Correct. All right. We good? Keep moving. So voltaic cells work because the reaction occurs as a result of the different abilities of the materials, such as the metals, to give up their electrons and the ability of electrons to flow through a circuit. In the example above, the zinc has an easier time losing electrons than copper, so it gives up electrons, and the equilibrium position of the zinc half reaction is further to the right. As a result, there is more push on the electrons from the zinc than from the copper, and the electrons will flow from zinc to copper when the switch is closed. That is, we turn the system on. The switch is on, for lack of a better term. This push is called the electrical potential. We'll get way more in depth of that in a second. This flow of electrons disturbs the equilibrium at each electrode, and the half reactions shift to either replace the electrons at the anode or use up the electrons at the cathode. And the difference in the electrical potential between the electrodes is called the cell potential, or the voltage, or the electromotive force, which I think for the College Board, they really only care about voltage or cell potential at this point. The EMF is minor. So, what does that tell us? That gives us something to think about. So if the cell potential is the potential difference between the two electrodes, that tells us that if the cell potential is larger than 0, it is a thermodynamically favored reaction, so the difference in the electrical potentials of the electrode is positive. So a positive cell potential means the battery or the electrochemical reaction is thermodynamically favored and it operates spontaneously. The more positive the difference, the more work the cell has the ability to do, the more voltage it can produce. A negative difference, so a negative cell potential, means the cell will not run spontaneously because there's not enough push on the electrons. Also, for two electrodes that differ by 1 volt, 1 joule of energy is released for each 1 coulomb of charge that moves between the electrodes. So in chemistry, we are defining a volt as 1 joule per coulomb in terms of units. Questions about that? Moving forward. Here are some examples of some voltages of some voltaic cells that happen to be in existence. Your common alkaline battery has a voltage somewhere around 1.5. You link two of them together, it becomes a voltage of 3. So they're additive. Your lead acid car battery, okay, has 6 cells. Each of those cells produce 2 volts, so it's a 12 volt battery. So that's the battery that's in your car. Your calculator battery, if it's a mercury one, like one of those button ones, you know what I'm talking about, those circle ones that are completely useless, right? Those have a voltage capability of about 1.3. The electric eel that you keep in your bathtub, each cell has about the ability to produce 1.5 volts. So a 6-foot electric eel has about 5,000 cells, electric cells, so it can produce 750 volts.
That's a lot.
That is a, hey, how's it going in the morning when you step in the shower, if that's where you store your pet electric eel.
Is that legal?
To have an electric eel?
Yeah.
I mean, I don't know. I don't know if electric eels are legal or not. But I mean, neither is like having a tiger, and some people do.
Yeah.
Okay? So, I don't know. I just wonder how one brings an electric eel home. Like in a cooler?
Rubber gloves.
What?
Rubber gloves.
Pair of rubber gloves?
I think.
Walking around like this with a
Yeah.
big electric eel going, "Wah." Okay, all right. And then the nerve of the giant squid. Now think about this. The nerve of the giant squid produces 0.07 volts. So that is the electric the voltage that can travel across the nerve. So that's the impulse of the nerve on the giant squid. We can measure our nerve impulses, but I guess really deep in the Animal Planet channel when I wrote this, so I should probably look that up at some point. But hey, here's some definitional stuff that you need to make part of your tattoo sleeve, perhaps. So standard cell potential. Note, we got this fun little notation here again. That means that we are at standard conditions. 1 pressure, 1 ATM for gases, 298 room temperature for the temperature, 1 molar concentration of solutions, and now we are adding pure solid electrodes is the standard cell potential. Okay. The standard electrode potential is a little bit different. Note the notation has the half cell. This is the potential for a certain half cell or half reaction, and it's measured when all components are in their standard states, which is always written as a reduction, and you'll see what I mean in a minute. Now, the formula to calculate standard cell potential is the difference between the electrode potential of the cathode and the standard electrode potential of the anode. So it goes cathode minus anode here. That's the formula that you should probably make part of your soul. Like with enthalpy, we can't know the absolute cell potentials. They're always known in reference to some standard electrode. And in our practical purposes, we use the standard of the hydrogen electrode, the SHE, whose standard potential is defined as 0 volts because it does not do anything. When comparing electrical potentials for two processes, the process that has more positive potential is the process that is more likely to occur. So we're going to talk about that in a little bit greater detail in terms of math in a second. Any questions about this definitional stuff? We good? Okay. So if we identify something to be a strong oxidizer, by contrast, it will be a weak reducer. And if something is a strong reducer, by contrast, it will be a weak oxidizer. This is very, very similar to how we viewed conjugate acids and bases. So you just have to keep that in mind. So I guess looking at the fluorine half reaction up above on top, it's a really strong oxidizer. Okay, and as a result of that, the fluoride ion is a weak reducer. And on the bottom, the strongest reducer is the lithium ion, and by contrast, it's a very weak oxidizer. Note the values. Positive value means it's thermodynamically favored. Negative value means it is not. Moving forward. by convention, electrode potentials are written as reductions. So we set them up so that they are written in a way that that reduction is occurring. In order for the cell to be a thermodynamically favored, the half reaction that is higher on the list has to be the cathode side, and it has to proceed as written as a reduction. And the half reaction that is lower on the list has to be the anode side, and it has to proceed reversed as an oxidation. I'll show you what that looks like in a minute. So in writing thermodynamically favorable redox reactions, the left side reactants must contain the stronger oxidizing reducing agents. So if zinc loses electrons to become zinc ion, the stronger reducing agent is the zinc. If the copper is gaining electrons to become the copper atom, it is the stronger oxidizing agent. So we always write them in the order of stronger reducing agent plus stronger oxidizing agent makes weaker oxidizing agent and weaker reducing agent. So we always write them in that manner. You have to make sure that the numbers of electrons involved in reduction and oxidation are the same. Multiplying the numbers of electrons does not change the cell potential value, since those are intensive properties. Those are always going to be the same no matter how much stuff is there. Questions about that? So we're going to do example number 5. A couple of things we need to keep track of here. We're given our reaction for the system as magnesium and aluminum in our system. And so our general reaction in this case would be something like magnesium solid plus aluminum ion, which would be aqueous, will react to form aqueous magnesium ion and solid aluminum atom. Okay, so that's basically what we're talking about here. So we're going to go ahead and use this formula we just talked about, but we have to remember that when it's written in this format, this tells me my anode, and this tells me my cathode. So when I'm given them, note that they are written both as what? They're written as oxidizing reactions or reducing reactions. Pardon? They're both written as reducing reactions. Do you see that? Okay. Now, so I'm going to go ahead and I'm going to use the formula that we just discussed. So the standard cell potential is equal to the standard reduction minus the standard oxidation. And so one of the things that might help in this case is if I would probably written it in a better color here. So let's see, reduce or reduction. So another way that we look at it sometimes to consider is the reduction side is occurring at the cathode, and the oxidation side is occurring at the anode. Now, so that means that when I'm going to go ahead and take my values and put them into the appropriate area, I'm going to take the E, the standard cell potential, and the value for that is going to be a negative 1.66 volts minus the negative 2.37 volts, and that will give me my standard cell potential to be 0.71 volts. And I remember back from about 4 or 5 slides ago, where if the standard cell potential is greater than 0, the reaction is thermodynamically favored. So in this case, because this is bigger than 0, this reaction is thermodynamically favored. So there's your homework for the evening. I am done for the day. Literally, have a good day.